Good morning. This is Vinod Kumar. I am working as a lecturer in electrical department in Government Polytechnic at Sirisilla. Sri Raja Rajeshwari Government Polytechnic at Sirisilla. So this one is the next level of the video lessons. Previous is video lesson is 18th completed. So on electrical engineering and electronics devices subject in electrical branch. So in previous videos we are explain about capacitors equations. Is capacitors connected in series connections. So derive the equation about the capacitors are connected in series, and derive the equation of the capacitors are connected in parallel, and derive the equation of the capacitors are connected in combination of the series and parallel circuits. Those are topics is covered in last previous videos. So next level of the videos. So next level of the video. So this one is a video lesson is 19. So next level of the video, the topic in this video lesson is energy stored in a capacitor. Energy stored in a capacitor. It's a very important topic in this video lesson. So energy stored in a capacitor. So already we are explained about the definition of the capacitors. So in previous video number 17 and 18, those are definition of the capacitors. So what is the types of the capacitors and applications of the capacitors. Okay, those are definitions and applications is covered in previous videos. And very important derivations about these capacitors. So those are derivations. So those are derivations is completed in previous videos. See the previous videos. So that's one is a derive the equation of the capacitors are connected in series. This slide, this PPT is a previous video PPT. So once remind this derivations and derive the equation of the capacitors are connected in series. One more topic is capacitors are derive the equation of the capacitors are connected in parallel, and derive the equation of the capacitors are connected in combination of series and parallel circuit. Those are important topics is covered in previous video lessons. So what is equation? The capacitors are connected in series. So one say in previous equations of the capacitors are connected. See these images about the capacitors are connected in series. So the equation of the capacitors are connected in series can say the capacitors are connected in series, that is the total capacitance 1 by C. So 1 by C means C is represented capacitor, it can be represented letter of the capital letter C. So C is a capacitor. 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So in this equation, 3 capacitors are connected in series. Can remind the equation about this. Capacitors are connected in series. 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So So remind this equation about capacitors are connected in series. Very important equations, and problem on this equation also. In next video lessons, I will explain about the problem one in this equation. And one more equations very important, that capacitors are connected in parallel. So this also completed in previous video lessons. So once remind the equation of the capacitors are connected in parallel, you can see the image of the circuit diagram. Here 3 capacitors are connected in parallel across the potential difference. You can see total capacitance, total capacitance, capital letter C is represented as total capacitance, equivalent capacitance. Capital letter C is represented equivalent capacitance or total capacitance. That is C is equal to sum of the capacitance, mean C1 plus C2 plus C3. Those are 3 capacitors are connected in parallel. So you can find the sum of the capacitance, total capacitance or equivalent capacitance, C equal to C1 plus C2 plus C3. So that's the equation of the capacitance are connected in parallel. Capacitance are connected in parallel. Then say one more equation about the capacitance are connected in combination of the series and parallel as per circuit diagram. As per circuit diagram, can you see the circuit diagram? Those are capacitors are connected in combination of the series and parallel as per circuit diagram. The equation of the capacitance are connected in combination of the series and parallel. You can see the images as per circuit diagram. 1 by C total capacitance, C in equivalent capacitance, 1 by C is equal to 1 by C1 plus 1 by C7 plus 1 by C8. What is C8? C8 is a combination. C8 is a C4 plus C5 plus C6, and C7 is a C2 plus C3. As per circuit diagram, total equivalent circuit is equal to 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Those are very important equations about this one. So in this video lessons, previous video lessons, that is a very important. Can remind the equation of the both of derive the equation of the capacitance are connected in parallel circuit, and derive the equation of the capacitances are connected in series circuit, and derive the equation of the capacitance are connected in both combination of the series and parallel circuit. Given in this video lessons, in previous video lessons, once can remind the derivations about the both are capacitance are connected in series and capacitances are connected in parallel, and capacitance are connected in series and parallel. Those are topic is covered in previous video lessons. Previous. So next level of the video lessons, so that video lesson number is 19. So next level of the video lesson, that video lesson of the 19, can see next topic to be continue on the video lesson number 19, energy stored in a capacitor. It's an important topic. So they derive the energy stored in a equation of the energy stored in a capacitor. The derivations also important, and problem on the energy stored in the equation very important. So we are explain in problem in next video lessons. So today we are explain about the only derive the equation of the energy stored in a capacitor. So can see on the PPT. So energy stored in a capacitor, can see the circuit. So once here in the circuit is a battery will be connected across the capacitor. The capacitor, it has a two plates two plates. The two parallel plate is connected across the battery through the galvanometer and switch. Through the galvanometer and switch. You can see the circuit diagram of the energy stored in a capacitor. You can see the image on the PPT in right side. It has in the circuit is a battery symbol, so that the battery is represented B letter, so and is connected across the capacitor, it represented C. So it capacitor in two plates, it can be establishing electric field, so and is connected in series with the galvanometer. So in the direction of the in circle arrowheads is represented the symbol of the galvanometer, so that is a galvanometer, and galvanometer is series with the switch. That switch is represented S letter, capital S letter. So that's the arrowheads is flow the electrons in the circuit. You can see the images of the arrowhead, so it can flow the electrons. See, in the energy stored in a capacitor, when a capacitor is being charged, it involves some of the losses of energy by charging agency. This energy is stored in the electrostatic field of capacitor. So when the capacitor is being charged, it involves some loss of energy by charging agency. Very, very important. See the definitions. When the capacitor is being charged, it involves some loss of energy by charging agency. One second. When the capacitor is being charged, it involves some loss of energy by charging agency. And this energy is stored in the electrical energy is stored in the electrostatic field of capacitor. You can see the image on the right side of the electrical energy stored in the capacitor circuit diagram. You can see. So let us, on discharging the capacitor, so the electrostatic field collapse and stored the energy is released. The electrostatic field is collapse and stored energy is released. So we are already explained about in charging in a capacitor and discharging of a capacitor. Charging of a capacitor and discharging of a capacitor. The topics will be completed in previous video sessions. So as is same circuit diagram. So has a same circuit diagram in energy stored in a capacitor and the discharging the capacitor, the electrostatic field is collapses and it can be stored energy is released. So the stored energy is released to the load. So let capacitance of a capacitor is C farads. It can be represented. So I will explain in definition. In the capacitance is represented each letter of the capital letter C. So that is unit of the capacitor. Unit of the capacitor is farads. Unit of the capacitor is a farads. So very important. So it can remind the, it can be represented the capacitors. It can be represented the letter of the capital letter C. So unit of the capacitor is a farads. Unit of the capacitor is a farads. In this circuit diagram, it has a two plates. Capacitor it has a two plates. The two plates is connected across the potential difference. A two plates connected across the voltage. So that is a represented sub potential difference, that is a represented capital V letter. Unit of the potential difference is volts. Unit of the potential difference is a volts. So let us the voltage across the capacitor at any instant is a, that is a V letter is a represented unit is volts. And charge acquired by the capacitor at any instant is Q coulombs. Charge acquired by the capacitor at any instant is Q coulombs. Q coulombs. Okay, Q coulombs. So charge acquired by the capacitor at any instant is Q coulombs. So generally, so charge is represented, Q letter is represented, Q letter, charge is represented Q letter, and the unit of the charge is coulombs. Unit of the charge is coulombs. So can remind this topic, these three sentences, that capacitors are connect. It can be represented capital letter C letter, and it can be measured in farads, and charge is represented the Q letter and measured in coulombs. And see in the circuit diagram, voltage across the capacitor at any instant is represented volts. Unit is volts. Potential difference unit is volts. And can see the circuit of the energy stored in a capacitor. So in supply voltage, mean V is equal to the work done. V mean voltage is equal to the work done, is shifting 1 coulomb of the charge from one plate to another plate. So very important, note this one. So voltage mean supply voltage is equal to the, or potential is equal to the work done. V is equal to the work done, is shifting of 1 coulomb. It can be shifting 1 coulomb of charge from one plate to another plate, one plate to the another plate. That is, work done is equal to supply voltage V into change of charge dq, V into dq, but Q in charge is equal to capacitor into voltage CV into Q is equal to CV. Okay, capacitor into voltage. So that is equal to change of the Q, change of the charge is equal to the C into change of the voltage dV. So you write as a, the work done D into W, change of the work done is equal to so dq you can substitute in C into dV, so that is equal to C V dV. So you can substitute in above equation, in equation change of the work done is equal to V into C into dV. And energy stored in the capacitor, can see the circuit, the total work done. So that is a represented work done is letter is represented W. So unit of the work done is joules. Unit of the work done is joules. So can see the circuit of this one two plate. The capacitor of the two plate is connected across the battery. So is through galvanometer and switches. You can see the circuit diagram in the PPT. And see the circuit diagram in this video lesson. Total work done, that is W equal to integration of 0 to volts, integration of change of work done, that is integration of range from 0 to volts, that is work done integration, that is equal to 0 to volts, integration of 0 to volts, change of work done is equal to CV into change of voltage, that is equal to C is common in bracket, so V square by 2, so that's range is 0 to volts, that is equal to 1 by 2 into CV square, 1 by 2 into CV square. C mean capacitor, square of the voltage. So unit of the work done is joules. So it's a very important formula about the equation about the energy stored in a capacitor. That work done is equal to W is equal to 1 by 2 into CV square, 1 by 2 into CV square. So unit of the work done is joules. Unit of the work done is joules. Okay. Energy stored in a capacitor. So that is the energy stored in the capacitor, that is called energy is E is equal to 1 by 2 into CV square, 1 by 2 into CV square, that is equal to Q square by 2C, Q square per 2C, unit is joules, can remain this equation and can be used in problem on the energy stored in a capacitor. In next video lessons we are practice on the videos, practice on problems, can see the circuit diagram and remain the equation about energy stored in the capacitor, that is equal to E is equal to 1 by 2 into CV square, that is equal to Q square by 2C, Q square per 2C, unit is joules. So we are already explained in Coulomb's law in electrostatics. So those are Coulomb's law in first law, second law. Those are also explained about this Coulomb's law of the electrostatic. It has two charges, positive charge and negative charge. Of course, positive charge and positive charge refer to each other. Both charges is same, so is can be refer to each other, and positive charge and negative charge is it can be attract to each other. In Coulomb's law, first law, like charges, you mean both charges will be same. Like charges is refer to each other, and unlike charges is attract to each other. Can see the image on the first law of the Coulomb's law. Can like charges is refer to each other, and unlike charges is attract to each other. Can see on image on the PPT. In second law of the Coulomb's law, force exerted between the two electrical charges is directly proportional to the product of their charges and inversely proportional to the square of the between the distance between them. Can remain this second law of the Coulomb's law. Force is exerted between the two electrical charges is directly proportional to the product of their charges and inversely proportional to the square distance of between them. So remains, and that is equal to Coulomb's in second law, that is force between the two charges in any media. That is, the force is represented F letter. F is equal to Q1 into Q2 per 4 pi epsilon r into epsilon r d square. So unit is Newton, force of unit is Newton. Therefore, between the charges in air, epsilon r is equal to 1, epsilon naught is equal to 8.854 into 10 power minus 12 farads per meter. So that is force is equal to 9 into 10 power 9 into charges q1 q2 per d square. And definition of the permittivity, those are completed in previous videos. So again I will repeat this topic of the permittivity and absolute permittivity. So what is permittivity? What is definition of the permittivity? What is permittivity? The definition, it is the property of the media through which it is allows the electric lines of flux to pass through it, or the ratio of the electric flux density D to the field intensity E letter is represented E letter. So ratio of the D to E, D mean electric flux density and E mean electric field intensity at a point is also called as a permittivity, that permittivity, therefore permittivity epsilon is equal to capital D per E. So in D letter is represented, so electric flux density, and E letter is represented electric field intensity. And absolute permittivity. Absolute permittivity is also known as a actual permittivity. Absolute permittivity is also called as a actual permittivity. Total absolute permittivity of air or a vacuum is minimum. That absolute permittivity epsilon naught is equal to 8.854 into 10 power minus 12 farads per meter. The actual permittivity epsilon of any medium of more than E naught. Actual permittivity is of any medium is more than E naught. So that is epsilon is equal to ER, that is epsilon R relative permittivity into absolute permittivity. Unit is farads per meter. And properties of the electric lines of force. So when see an image, so this electric lines of force can flow from positive to negative. They are imaginary lines of force. Can see on images, imaginary lines of force positive to negative. Its arrowheads can flow from positive to negative. They start from positively charged body, they end at a negatively charged body. So the charges will be flow from starting from positive charged body to negative charged body. They never intersect each other. They are elastic in nature. can see the imaginary lines of force, electric lines of force, imaginary lines of force. They are flow from positive charge to negative charge. They never be intersect to each other. They are elastic in nature. They are elastic in nature. See the electrostatic lines of force. The positive charge, this is a magnetic lines of force. Previous one is a electrostatic lines of force. A magnetic lines of force. What is the difference in two circuits? This is a magnetic circuit. This one is a electrostatic lines of force. You can see the images and difference. Say magnetic lines of force, electrostatic lines of force. Two different circuit of the magnetic lines of force. See the difference, very important about the comparison between the electrostatic lines of force compare between the magnetic lines of force. The two comparison between are difference between the magnetic lines of force and electrostatic lines of force. And it difference between two topics, magnetic lines of force and electrostatic lines of force. Very important topic. So see the comparison between the electric lines of force and magnetic lines of force. So this question is asking for board examination. So many times is asking for board examination. So that is the electric lines of force and magnetic lines of force. So in electric lines of force, you can see a positive or negative charge establishes electrostatic lines of force. A positive or negative charge establishes electrostatic lines of force. In magnetic lines of force, a current carrying conductor establishes magnetic lines of force. Current carrying conductor establishes magnetic lines of force. In electric lines of force, it can be developed the electric flux. In magnetic lines of force, it can be developed the magnetic flux. In electric lines of force, electric flux density, it can be represented D, capital D is equal to, so electric flux per area, Coulomb per meter square. Magnetic flux density, beta is equal to magnetic flux per area, Weber per meter square. Weber per meter square. In electric lines of force, the permittivity epsilon is equal to absolute permittivity and relative permittivity. That is absolute permittivity, therefore absolute permittivity epsilon naught is equal to 8.854 into 10 power minus 12 farads per meter. Permeability mu is equal to mu naught into mu r. Absolute permeability or relative permeability. In absolute permeability, mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. And electric lines of force, these lines don't form closed path. do not form closed path. In magnetic lines of force, these lines form closed path. They are is normal to the surface. Electric lines of force, they are normal to the surface. Magnetic lines of force, they are not normal to the surface. Electric lines of force, these lines do not pass through the conducting substances. In magnetic lines of force, these lines pass through the conducting substances. In electric lines of force, isolated positive or negative charge exists. In magnetic lines of force, isolated north or south poles does not exist. So those are difference between the comparison between the electric lines of force and magnetic lines of force. So very important. So that is, in see electric lines of force. So I will repeat again this one. So comparison between the electric lines of force and magnetic lines of force. In electric lines of force, note on very important comparison. So in positive or negative charge establishes electrostatic lines of force. Electrostatic lines of force. In magnetic lines of force, the current carrying conductor establishes magnetic lines of force. In electric lines of force, it can be developed the electric flux. In magnetic lines of force, it can be developed the magnetic flux. In electric lines of force, electric flux density D equal to electric flux per area. And in magnetic lines of force, the magnetic flux per area, magnetic flux density, magnetic flux per area. Unit is Weber per meter square. Weber per meter square. Next, permittivity. Permittivity epsilon is equal to absolute permittivity and relative permittivity. Absolute permittivity and relative permittivity. So therefore, absolute permittivity epsilon naught is equal to absolute permittivity epsilon naught is equal to 8.854 into 10 power minus 12 farads per meter. Farads per meter. Relative permittivity in air is 1. So in permeability in electric lines of magnetic lines of force, permeability mu is equal to mu naught into mu r. Absolute permeability and relative permeability. Absolute permeability 4 pi into 10 power minus 7 Henry per meter. In electric lines of force, these lines do not form closed path. Do not form closed path. In magnetic lines of force, these lines form closed path. Lines form closed path. In electric lines of force, they are normal to the surface. So in magnetic lines of force, they are not normal to the surface. And electric lines of force, these lines do not pass through the conducting substances. In magnetic lines of force, these lines pass through conducting substances. And electric lines of force, the isolated positive or negative charge exits. And magnetic lines of force, the isolated north or south poles, north and south poles does not exits. So this comparison about the electric lines of force and magnetic lines of force is asking for board examinations. Is sometimes is asking long question and short questions also. So is remain this problem, question. And so in this video lessons, mainly we are explanation about the derive the expression about the energy stored in a capacitors. So derive the main thing in this video lessons. In previous video lessons, that derive the equations of the capacitors are connected in series connections, and derive the equation of the capacitors are connected in parallel equation, and derive the equation of the capacitors are connected in combination of the series and parallel circuits. Those are derivations is completed on previous videos, and in this video lessons is main thing is derive the equation of the energy stored in a capacitors. So in these derivations and previous derivations, those are derivations very important. So this problem on this derivation in different derivations at problem can be solved on next level of the video lessons. Next level of the video lesson number 20. So we are solve the problem on these derivations. Okay, so we are solve the problem on derivation of derive the equation of the capacitors are connected in series, that is 1 by the equation of the capacitors are connected in series, 3 capacitors are connected in series, that is equation of the capacitors connected in series 1 by C is equal to 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3, that is equation equivalent capacitors are connected in series, that is remain the equation very important for use for problem. And the capacitors are connected in parallel, and derive the equation of the capacitors are connected in parallel. So that is equation of capacitors, that equivalent capacitor is represented C, that capacitor 3 capacitors are connected in parallel, that is a C1, C2 and C3. So you write the equivalent capacitance C is equal to C1 plus C2 plus C3. Okay. And one more derivations of the derive the equation of the energy stored in a capacitor. So the derive the equation of the energy stored in a capacitor, that represented the E letter, that E is equal to energy stored in E equal to capital letter E is equal to 1 by 2 into C V square, capacitor into voltage square of the voltage. So E is equal to 1 by 2 into CV square, that is equal to Q square. Q means charge, unit of the charge is coulombs, Q square per 2 into equivalent capacitor, total capacitance 2C, Q square per 2C. So unit of the energy stored in a capacitor is joules. Unit of the energy stored in a capacitor is joules. So it can be remain the equation about the energy stored in a capacitor, simply equations, and by head this equation of the energy stored in a capacitor, E equal to 1 by 2 into CV square or Q square per 2C, unit of the energy stored in a capacitor, joules. Unit of the energy stored in a capacitor, joules. So very important equation can remain the equations. We are solve the problem on next video lessons on this derivations. So number of the problems, exercise problem and example problems we are solve on next video lessons, and video lesson number is 20. So we are practice on next video lessons. Okay, so once I will remain the equation of the energy stored in a capacitor, the E is equal to 1 by 2 into CV square or Q square by 2C. Unit of the energy stored in the capacitor is joules. So we are problem will be solved on these derivations on next video lessons. Thank you.